Hello everyone, my name is Ahmet Sartokur. I'm teaching assistant for hydromechanics course. Today I'm here to conduct our first lab experiment. But before I start, I would like to mention some brief information about our experiment. If you look at your handouts, first page, you will see there is an objective and theory part in the beginning. Basically, the objective of this experiment is to determine minor and major head losses through this system of pipes.
Okay, now let's talk about a bit from the theory part of the experiment. Characteristics of a fluid can be decided based on its Reynolds number. As you know, if the Reynolds number of a fluid is less than 2100, it is considered as laminar. If it is more than 4000, it is considered as turbulent flow. In our handouts, there is a formula here to calculate Reynolds number, which is here. In this formula, ρ is the density of the fluid, V is the average velocity of the fluid, D is the diameter of the pipe, and nu is the fluid viscosity. In a steady flow, viscous effects can be incorporated into Bernoulli equation in terms of a head loss. What that means is that basically we can use Bernoulli equation to find major and minor head losses. Here you may ask, what is a major or minor head loss? Simply, losses happening in a pipe due to its surface roughness and length are considered as major head losses and shown as H major. On the other hand, losses happening due to fittings, junctions, and elbows are considered as minor head losses. There is an extended Bernoulli equation provided us to calculate major and minor head losses, and just below that we are given two different formulas for H major and H minor. In these formulas, F is the friction factor, L is the length of the pipe, G is the gravitational acceleration, and K is the loss coefficient. When we go to the next page, you will see there is a Moody diagram is provided us. On the x-axis of this diagram, the Reynolds number stands, and on the y-axis, the right one, it's roughness, and the left one is the friction factor. Once we calculate the Reynolds number, we can get friction factor by using this diagram. How we are going to do that is, firstly, we need to calculate the Reynolds number by using the given formula in the handout. Then, if the Reynolds number is less than 2100, as you know, it is considered as laminar flow, so we will check this curve. If it is more than 4000, this time it means that our flow is turbulent, so we will need to use one of these many curves. In turbulent flows, there are many different curves for different roughnesses. However, in this experiment, since our pipes are smooth, we need to check only this curve, which stays at the very bottom and shown as smooth, and that will be enough for us. So in general, we can say that the relationship between friction factor, Reynolds number, and pipe roughness can be estimated from Moody diagram. When we move on to major head losses, we have two different friction factor equations. The first one is when the Reynolds number is less than 2100, and the second one is for when the Reynolds number is more than 2100. When we move on to minor head losses, we have again two different scenarios. In the first scenario, we have banded and angled pipes. In this scenario, if the radius of the band is more than the pipe diameter, like in the first picture, it is called pipe knee piece. If it is less than the pipe diameter, it is called pipe bend, like in the second picture. If two pipes are added one to another but didn't bend it, it is called pipe angle, like in the third picture. In the second scenario, we have expanded and contracted pipes. The change in cross-sectional area can cause discontinuous expansion or contraction. For a discontinuous change in cross-section, the loss coefficient, which is K, can be derived using the extended Bernoulli equation and the mass conservation principles. As you see, we are given a formula here to calculate this K value for the second scenario. In this formula, D2 is the larger diameter and D0 is the smaller diameter. You will be using these equations when you start writing your reports.
I want to continue with the setup descriptions. It's on page 4 in our lab manual. In here, I would like to introduce you our device before we conduct the experiment. If you look at bottom right side, you will see there are some numbers and names for the parts of our machine. Number 1 is called the pressure tapping labs. They are these parts, as you can see. This is where we are going to measure our exact heads during the experiment. Number 2 called ball cocks. These are these parts. I prefer them to call valves basically because it's way easier to remember. Number 3 is not important, it's just a backside valve. Number 4 is called double pressure gauge. We have one on the left and one on the right. We are going to use this part to read our heads during the experiment coming from these pressure tipping nipples. Number 5 is the inlet. Inlet is the part where we are going to let water inside the system. And number 10 is drain, where we are going to let water outside the system. The number 6, 7, 8 and 9 are not related with this experiment. Now I would like to introduce you which section are going to be used for what. As you see, we have 1, 2, 3, 4, 5, 6 different sections, 6 different pipe sections. In this experiment, we are not going to use section 3, 4 and 6. We are going to use only section 1, 2 and 5. Section 1 are going to be used to determine head loss through a sudden expansion and sudden contraction. As you can see, this pipe is thicker, these are thinner. Section 2 is going to be used to measure head loss through a long smooth pipe for a major head loss. Section 5 is going to be used to measure head loss through a 90-degree bend, 90-degree knee piece and 45-degree angle pipe. Before I start the experimentation, I would like to give you some brief information about what we are expecting from you to write in your reports. If you turn on page 7 in your handouts, you will see there is an analysis and report questions part. In the analysis part, we are expecting you to estimate some Reynolds number and comment on it if the flow is turbulent or laminar. We are expecting you to obtain friction factor or loss coefficient by using Bernoulli equation. We want you to, after that, estimate some friction factor and loss coefficients using the data measures, which I will send you by email. And then at the end, we want you to plot the friction factor and Reynolds number graph. In report questions, you see there are several questions in this section. We want you to answer all of them in this part. Now I would like to continue with the experimentation part. Before I turn on the machine, I have to make sure that every valve is closed in the beginning. Then I will come here and start the device. Before we take some measurements, we have to make sure that all the air bubbles in the system are drained from the machine. To be able to do that, I will take these two hoses, which is connected to the pressure gauge, and put them in random pressure thermometers. Now I will open this valve connected to section 1 pipe. As you see, water is coming inside. From here, when I open this valve, water will start to get out from the system. And of course, I also have to open this valve. You can see water is coming out. To clear those air bubbles inside the system, several times I will close the valve and then open it again. You see bubbles are going inside. I can also do it from here. After we finish cleaning the air inside the system, we can start our real experimentation. After cleaning the air bubbles, now I would like to conduct the real experiment and show you how to take some measurements. To be able to do that, I will take these two hoses connected to the pressure gauge and put them some random points where I want to take some measurements. Let's say I want to see the friction loss happening through this pipe in section 2. For that, taking this hose connected here, and I'm taking this one connected here. Before I open this valve, I want to see these water levels inside two tubes are leveled. They should be equal before I start the experimentation. The first one I connect becomes our upstream, and the second one I connect becomes our downstream. Now I'm opening the valve. I'm also opening these drain valves as well. You will see water level will start changing. As you can see, there is almost this much difference in water levels. This is mainly because of the head loss happening due to friction. Now I'm going to close the valve. And change the location of these hoses, because I want to show you that when I reverse the locations, also water levels in the tubes will be reversed. Now I'm opening the valve and opening these valves as well. Sorry, I opened them. As you see, this time inside the water level, which is in the right tube, is way higher compared to left one. We basically reverse the situation. Now I'm going to turn it off them again. Lastly, before I finish the experiment, I will put a 5-liter bucket here, as you see. There is this red sign. I will fill this bucket till here, and I will take the time required to fill 5 liter water inside this bucket. So it will be our delta T. By using delta T and our volume 5 liter, we will be able to calculate our discharge, and we will be able to calculate our velocity because we know the diameter of these pipes. Then you will be able to calculate Reynolds number and whatever is needed in the lab report. Now I put this bucket here. When I open this valve, water will come from this pipe, and when it reaches this level, I will stop recording the time, and we will see that is our delta T. Okay, let's start. 1, 2, 3. Okay, it's around 10 seconds.